So, I am guessing I'll sometime either late Wednesday. I would like to just devote whatever time we have left to reviewing whatever you'd like. I posted a new set of problems from the book to Canvas recently for you to take a look at, or just from the last two sections. But remember, the final is comprehensive. So anything you want to talk about, we can go over on basically whenever there's time to do so. So if you haven't already looked at that, the Canvas area with all the review stuff I've identified, please do so. But you will most likely get plenty of time to ask whatever questions you want later this week. Any questions on that or anything else before we get started? All right, so we've been talking about definite integration, how to evaluate those using antiderivatives. Mostly using the idea of area to kind of ground that. But let's look at another interpretation. So basically what we've done so far with the evaluation theorem of definite integration is, if you want to integrate a function, you just need to evaluate the antiderivative of that function over the endpoints of that interval. We've mostly been using this in terms of area. We can use this for pretty much any situation if we think about it like this. Before, what does the derivative function tell you about that problem? Cameron?
The slope.
Tells you the slope. What else? Sebastian? Slope of the tangent line? Anything else? Not necessarily related to. I mean, it's related, but it's a little more abstract, I guess. Go ahead. I can tell you something about critical points if you are interested in what the derivative is specifically valued at. Go ahead. Could be velocity, and that's kind of the example I'm hinting at here. But in general, we've talked about the derivative as this idea of an instantaneous rate of change. So whatever the function tells me the instantaneous rate for whatever value of x I want to choose, whatever value of x I want to look at it. So let's kind of put that into something more concrete. Actually, what I should say there is this: if you know the exact rate of change of a thing, of some idea over some interval, then you can tell me by exactly how much that thing has changed. So in this bottom example here, if I'm calling v a velocity, and I know what the velocity is at any time, and I'm looking to integrate that velocity over a 30-second interval, then what am I going to get? What is that 100 right there going to represent? If I have velocity, what is velocity the rate of change of? It's the rate of change of distance over time, right? So if I know something about this velocity function, and I integrate that velocity function from t equals 0 to t equals 30 seconds, and I get 100, what does that 100 tell me? Like, what does that 100 represent? Yeah, so that's exactly it. So I've traveled 100. Did I give you a unit? No. 100 distance units, meters, feet, whatever units we're measuring that in, but that's exactly right. So if velocity changes distance over time, or displacement over time, which by definition is, we integrate that rate over time, then I will get a distance. You mentioned displacement, yeah. So I didn't know if that was. So, let's talk about the difference there. So let's say this is velocity over 30 seconds. Let's say, for example, this velocity is like this. If I were to integrate that, basically area, right? In that case, distance and the displacement is going to be equal. In this case, it will, because really this object is only moving one direction. It's only moving in whatever the positive direction is. And this kind of goes back to what we've talked about signed area. So let's say instead we have a function like this. The velocity looks like that. And especially for those, let's make a function that's actually a function. Closer. And those of you who are taking physics or will take physics, which is probably the majority of you. Now, what does that 100 represent there? In this case, it's not going to be equal to the total distance. It's a very... Yeah. It's the displacement. So basically, if I'm saying this is 100, basically what I'm saying is in 30 seconds, this object is now 100 units away from wherever it started. But look at the path it took. It was going, if we think of upward velocity being forward and downward velocity being negative, probably traveled a lot further than 100 units. So remember we talked about signed area in the last week? So we had an example where we took the area between the graph of a function and the x-axis, but really what you had we had a lot of there was we had a lot of positive areas and a lot of negative areas, and there just ended up being more positive areas. You have the same kind of phenomenon here. All right, any questions before we move on? Okay. So basically that's the net change interpretation, which basically we just talked a lot about this. If you know the exact rate of change of some quantity, you can integrate that rate of change to get what the actual change in that quantity is. So let's apply that to straight line motion here. I have a particle moving along a straight line, and there's its velocity. I want to know what its displacement is. So basically, how far is it going to end up? How far away is it going to end from where it started? Go ahead. I'll go back real fast, but it was so the same mathematical equation. Basically, we're looking at it in this curve. Yeah. We can look at this and this derivative as, that's what a derivative is in relation to a function. The derivative of a function tells you its instantaneous rate of change for any value of its input. So now we can relate that to an integral. Cameron?
So this net change gives the displacement?
This right here is very general. If you're talking about velocity, this would be like the flow rate of water. If the derivative was the flow rate of water from the pipe, what would be? So if I know how much water it is, if I know the rate of change of water flowing through some pipe, then I can integrate over that and get the actual volume. All right, so I want to find the displacement of this particle. I know its velocity for any value of time. I want to find the displacement over this specific little 3-second interval of time. So based on that net change interpretation, how would I find this? So that thing that you're describing, what is that? That's the integral. So we're going to integrate the function over the integral or the interval 1, 4. So let's just take this slow. T squared minus t minus 6. All right, so this will give us the displacement. basically, I'm going to find out where this object was at 1 second, where the object was at 4 seconds, and find the difference. But to do that, how do I have to continue this? Yeah. What is the antiderivative of this expression? 32 cubed. 1/2 t squared. Do I need the plus c though? For a definite integral, I know that whatever constant I assign to this is going to end up getting annihilated as I subtract it. So now evaluate this from 1 to 4. I got 1/3 times 64. This 1/2 times 16 minus 24 minus the expression evaluated at 1. So 1/3 minus 1/2 minus 6. And let's go ahead and approximate. Let's leave let's evaluate to the 2 decimal places per se. I got this number, but I really don't trust it. Unless someone wants to verify it. All right, did I give you a unit here again? No, let's say it's meters. So I got negative 4.5 meters. What does that mean in this context? Total displacement was negative 4.5 meters. Over that specific 3-second span, the displacement was negative. What does it mean for the displacement to be negative, Cameron? Yeah, he went backwards. It went backwards, whatever it is. Was it going backwards the whole time? Yeah, we don't know that yet. We could probably find that out pretty easily, but we don't know that. Was it going backwards at some point? Clearly had to do that. So this velocity was negative somewhere, but maybe it wasn't negative everywhere. So that gets us into our next idea here. Now I want to find the total distance traveled. So our total displacement was negative, right? Yeah. Let's talk about the definitions of the difference between distance and displacement here. Can distance, in a physical, mechanics context, can that be a negative number? Whatever the distance you move is always increasing. If I were to walk one, definitely had some movement as I walk around. All right. So if I want to find total distance here, what do I really need to know? Like, what other information do I need? I need to know when the velocity is positive and when the velocity is negative, right? So how can I get that based on? So if I can do this, integrate the absolute value. Here's the problem with doing this. I mean, it's a small problem. Everything we know about finding integrals right now it deals with, you have to have a function that's differentiable. And one thing we talked about, absolute value function is not differentiable when it equals 0. So this is the integral we're going to find, but we can't do it directly like this. That will get me an estimate, but I can do this exactly. So back to the reason this absolute value doesn't work. The absolute value is going to be hard to get at directly because there are probably places where the velocity is equal to 0. Can we find those places? Let's do that. So if I set this velocity equal to 0, what does that factor to? Plus 2t minus 3. All right. So I got the velocity is equal to 0 at -2 and 3. Do I care about both of those? I just care about 3. So I know that when time is equal to 3, the velocity is equal to 0. So does that help me? Can I rewrite this integral in some way that I can actually compute it? Okay, so I'm going to take 2 separate integrals, right? So I'm going to integrate this thing, integrate this other thing. Are my intervals going to be the same? Okay, but I at least know what those intervals are now, right? Okay, so I know I'm looking at, and I can use this thing for all kinds of stuff. I know that, okay, I only care about time values from 1 to 4. I know that at 3 seconds, the velocity is 0. But yeah, you're right. I need to know on which one, if the velocity is positive or negative on these intervals. So what's a good test point to use for the first little subinterval here from 1 to 3? Why not 1? I just might as well use the end of the interval. I know that velocity at time 1 is equal to 1 minus 1 minus 6 is equal to -6. And at 4 seconds, it's equal to 16 minus 4 minus 6 is equal to +6, right? Yeah. We okay with that? Okay. So now, this first I'm going to integrate from 1 to 3. What am I going to get when I integrate v of t over that interval 1 to 3? I'm going to negative value, right? So I'll give you a couple choices here. We can either integrate it as is and know that we just need to flip the sign of what we end up with. Or what I vote we do the first time is just integrate the exact opposite of it. Because basically what we've learned here is this, and I think it's helpful to look at a graph. We're looking at time from 1 to 4. This is a bad way to draw this graph. It has negative values. From time 1 to time 4, basically what we know is this: our velocity is going to act like this somewhat. So we're going to get an area below the x-axis and an area above. So if we want to find that area below, we know if we were just integrate v of t, we would get a negative number because that's how a Riemann sum, or that's how a definite interval works. So in order to get the positive number that we're actually interested in, we can integrate the opposite of it. So I'm going to integrate from 1 to 3 of this: -t squared plus t plus 6. Let's set up both integrals before we actually do one. So that's the first subinterval. What are we going to integrate for the other part of this? 3 to 4. And just VT, or is that, or should I change it somehow? Yeah, that one's going to be as is. So for this one, I'm going to integrate from 3 to 4 of the function that I gave you, t squared minus t minus 6. All right, before we compute those, any questions on how they were set up? Sebastian? Right. Yep. And kind of back to the way, I think this was Cameron's idea. She wanted to integrate over the absolute value. Think about what this graph right here that I drew would look like if this was actually the absolute value of VT. Then this area right here would be mirrored above like that, right? And you can, but you can't use one integral. Because basically our only weapon for dealing with integrals, we have to integrate functions. Those things aren't differentiable. Let's see if I can illustrate that. If you were to find the slope of the tangent line at t equals 3, what goes wrong for you? I didn't mean for that to happen. It's not necessarily a vertical line, but the limit. So let's go way back to the beginning of the semester. Remember, the derivative is really just a limit. That limit from the left of 3 is going to be different from the limit approaching from the right. So that derivative doesn't exist. So that means that the whole antiderivative approach to this is going to fall apart, which is why we have to use this antiderivative, or this partition the interval in this way. I think that's a really important point. So if there are more questions about that, keep them coming. All right, we ready to take an integral? All right, all right, so let's do the one on the left first, from 1 to 3. How do we continue? Antiderivative, which is not 1/2. There you go. Plus 1/2. From 3 to 1 gives us negative 1/3 of 27, which is negative 9. Plus 1/2 times 9, so plus 9/2, plus 18. Minus all of this, minus 1/3, plus 1/2, plus 6. Since I know you know the antiderivative, so I'm gonna go ahead and just catch up with you. But yeah, someone calculate these things for me. What's that? Go for it. 9 1/3 for the left one. Okay. Cool. All right, and then this one, where do I leave off? Right, and this one, this right bracket, this final bracket quantity should be 0. (64 thirds). Why did it come out negative? Should have come out positive, right? Something, so. No, I think it's gonna come out negative, but why? Yeah, maybe I did that wrong. I thought that this came out to be 0, unless I just computed it wrong. 1/3 of 27. Oh,
It's just the other one, but on the side.
yeah, I did something. Yep. Right. Does anybody have a number here? One third of 3 cubed. 3 cubed is 27. So this line right here is t equals 4. This one here should be t equals 3. Yeah. 2.83 repeating. That's what, 2 5/6. All right, so what do we get for our answer for the displacement on this? Negative 4.5. Does that jibe with what we got here? Because really the difference between these two things here. So we know that as this object is going backwards, it covers 9 1/3 units of distance, right? That's what that first integral tells us. And as it's going forward, it covers 2 5/6 units of distance. So is the difference between those two things 4.5? Right. So does it make sense why I'm asking if they are different by 4.5? Sebastian? Well, I think that's what we expect from. Basically, the displacement tells you the difference in those two areas, if we think about this in terms of area. So I'm wondering where the mistake is, because from the displacement, I would have expected. From the displacement, I would have expected those two areas to be off by 4.5. So let's look at this one again. I think this one is okay though. Yeah, let's verify. Yeah, I got -4.5 for that one. But these are off by 6.5. So there's got to be some problem here. But does it make sense why these figures have to be off by 4 1/5? If we're trusting our displacement, which I think we should. What'd you get? Yeah, and that's the part that bothers me, because that shouldn't be negative. Did we do the antiderivative wrong? I don't think so. I think it should be positive 7 1/3, right?
Yeah.
Okay. Oh, right. Okay, that makes sense. All right, so basically the total distance traveled in the opposite direction for the first 2 seconds, for 7 1/3, and then in the last second, the distance was 2 5/6. So what does that say then about total distance? Distance total is equals 10 1/6, or 61/6. All right. So I kind of had some hiccups there, but any questions about anything we've done? Are we okay with the distinction between displacement and distance? Sebastian? 10 1/6 or 61/6? So basically, what am I going to do? So now that I have these two like sub distances, what do I do with them? Just add them together. Anything else about this? All right. That's all I have for you on 5.3. I put a due date for this already. I think it's Wednesday night. Go ahead and move on to 5.4. All right, 5.4 is all about something called the fundamental theorem of calculus. Which is the evaluation theorem, basically what we've been doing to evaluate definite integrals, is very, very related to. So let's look at this function. So we got two functions related in this way. We're going to let f of t equal 2t, and this function capital A of x is basically a function that's defined using an integral. So this is just kind of a warm up to get us to think about the fundamental theorem of calculus. But let me write down what A of 0 is going to be defined as. And one thing that's going to be useful to pay attention to here is one function is defined in t, the other function is defined as a function of x. So one thing we're going to need to keep track of is basically keeping those two things separate. So A of 0 is going to be equal to the integral from 0 to 0 of 2t dt. What should that be equal to? So remember, it's going to be a number, right? Why do we know it's 0? Do I even need to take the antiderivative in this case? No. Yeah, the integral. So if the interval has no width to it, then the integral has to be 0. So let's go a little further. What is A of 1 going to be? Now it's an integral from 0 to 1 of 2t dt. How'd you get 2? It should be 1, right?
Oh, yeah.
All right. Let's go again. See if we see anything emerging. What's the antiderivative from, or the integral from 0 to 2 of 2t dt? Same antiderivative, right? So this should be 2 squared minus 0 squared, which is equal to 4. We have a suspicion about what A3 and A4, A of 3 and A of 4 are going to be. You okay with that? Yeah. 3 squared minus 0 squared is going to equal 9. And then, yeah. So based on all that, can I generalize what a of x is? And close. I'm going to say x squared since a is a function of x. Is it plus c though? If I were to just ask you for the antiderivative of 2t, then I think you have to say t squared plus c, right? But in this case, why is there no plus c here? Let me try to collect all these things in a table. So x versus a sub x, or a of x. So when we have that, we have to have that constant of integration. What kind of integration are we doing where we have to have that unknown constant of integration? Was there, yeah, it doesn't, or antiderivative or an indefinite integral, right? Is this an indefinite integral? That's what I wanted. What makes one what distinguishes definite integrals from indefinite ones? What? Right. So that's true, but why does the definite integral give you a value? Right. It has limits of integration. And this one, even though I let one of them be a variable, it definitely has limits of integration, right? This would have been different if I would have made this lower limit -1, right? In this case, we would have had a constant, we would have been able to find it. So any questions about how these two functions are related or how we got this a of x equals x squared? All right, so let's look at, you'll see a few different flavors of fundamental theorem of calculus. We're going to focus on one in this class. But basically, the fundamental theorem of calculus, it has such an important sounding name because it is. I mean, there are two huge branches of calculus, differentiation and integration. This is the theorem that unites them. So if I have some continuous function on some closed interval, and I have this function here, so I have some function within an integral. If I integrate over that function, keeping this that upper limit general, those two functions are united in this way. So up until now, we've looked at functions, just functions in and of themselves now, or functions in and of themselves separate from integration. Now we're kind of bringing those things together. So that function a is an antiderivative for f. Or if you say that in the opposite way, in the inverse language, a prime of x is equal to f of x on this interval. So if we can tie this back to what we just did. So we recently had this, right? So the integral from 0 to x of, what was f of t, 2t dt? In general, when you're doing a definite integral, how would you handle this definite integral on the right here? If I want to integrate from 0 to x of 2t dt, what is the antiderivative of 2t? So that would be equal to t squared. And then what would I do with that t squared? Right. So I'm going to evaluate it from 0 to variable x, right? If I evaluate t squared at x, what do I get? Right, you're just plugging in x for t, right? So that becomes x squared. If I evaluate it at 0, what do I get? 0 squared. So does that make sense with what we got before? So we kind of took the long way to get there, but helps to illustrate how this theorem works. Any questions so far? All right. So let's handle a concrete case of this. So let's rewrite this based on what I have. So I'm saying g of x is equal to the integral from 1 to variable x of q squared dt. So right here, this is what's usually called an open form for g of x. I mean, it's a little hard to compute with this because, you know, even going to a calculator with this is kind of hard because setting up an integral takes time. What we'd like to do for g of x is get to what's called a closed form. I just want to get to basically an expression. So how could I handle that for g of x here? Or something else I want to ask is, do we know what the derivative of this thing is going to be? What's the derivative? So close. Your t squared was closer. So okay, let's work up to it. It's going to be x squared. So it's okay if you don't understand why that is x squared. I mean, this is a brand new theorem, just learning how to apply it, but hopefully by the time we get there, it won't be a surprise. So let's handle g of x first. We've been talking about how to deal with integrals for several days now. How do I handle this definite integral from 1 to x of t squared dt? Yeah. So, I mean, don't lose sight of that. The last theorem we just spent a lot of time in, that evaluation theorem. We still need antiderivatives, and we still need to evaluate the antiderivative at the ends of the interval. So what is the antiderivative of t squared? 1/3 t cubed. And I evaluate it from 1 to x. And what do I get? One-third x cubed minus 1/3, right? So this is what g of x is equal to. And basically, you know, we've been using the fundamental theorem of calculus for a few days now. The evaluation theorem is not much different from it. Any questions on how we got g of x? How is g of x related to g prime of x? Right. Does that derivative there make sense with what we have for g of x? But is there any way we could have known that g prime of x is just equal to x squared straight away? Right. So, I mean, the whole motivation for the fundamental theorem of calculus is that derivatives and integrals are related in a very specific way in this inverse relationship. So if I tell you that g of x is equal to some integral, and then I want g prime, wouldn't it make sense that g prime is just whatever the function is that you're integrating? That's exactly why g prime of x is just equal to x squared. Question? Let me unpack that a little bit. So remember This just goes back to what we call the evaluation theorem. If you want to integrate some function over an interval, you find the antiderivative of that function, so 1/3 t squared or t cubed, and then you evaluate that function at both the endpoints. In this case, the upper endpoint is x and the lower endpoint is 1. So 1/3 times x cubed minus 1/3 times 1 cubed. Better? Cool. All right, any questions here? All right. I think we can do this next 3 minutes. What's the derivative of this function here? There you go. And that's a direct application of the theorem. Let's say you didn't recognize that. Unfortunately, the function square root of 1 plus t squared is not something that we have the tools to take an antiderivative of yet. But do we know that it has an antiderivative? Yeah. So let's say this. Let's say f of t is equal to square root of 1 plus t squared. I don't have a way to figure out what capital F of t is, but I know that it exists, right? So because of that, I can do this. G of x is equal to the integral from 0 to x of f of t dt. And I know from the fundamental theorem of calculus this is going to be equal to this capital F of t evaluated from 0 to x, which is equal to the capital F of x minus capital F of 0. From there, what's the derivative of g? What's the derivative of capital F of x? And it's just equal to lowercase f of x, right? What's the derivative of capital F of 0? Why is it 0? Right, so even though I don't know what the antiderivative of f is, I do know that when I just evaluate it at a single number, it's going to be a constant, right? So because of that, it evaporates. So we got the g prime of x is equal to f of x, which by our definition is radical 1 plus x squared. Go ahead. Good catch. No. As long as it is a constant. Any other questions here?
Yeah.
Go ahead. Yeah, so f of 0 is a constant. Because capital F is a function, right? So if I plug in a single real number to it, I will get a single real number back. What's the derivative of any constant? Yes. So I'm not saying, yeah, the derivative of this thing is equal to 0. I don't know what that constant is. I don't have a way. This constant. Okay.